I'm going to perform a t-test using this example from the book. Georgiana claims that in a small city renowned for its music school, the average child takes less than 5 years of piano lessons. We have a random sample of 20 children from the city with a mean of 4.6 years of piano lessons and a standard deviation of 2.2 years. Evaluate Georgiana's claim, or that the opposite might be true, using a hypothesis test. Georgiana wants to know if the mean number of years the children spend taking piano lessons is less than 5. So she should be doing a one-sided test if that's her alternative hypothesis. But part A is instructing us to perform a two-sided test, so that's what we'll do. The null hypothesis is that the population mean years of piano lessons is 5 years. We have H0 mu equals 5. The alternative hypothesis is what we want to show. We're doing a two-sided test, so our alternative is HA mu does not equal 5. We're given everything we need to compute the t-statistic. We're told that the sample mean is 4.6, and we're told that the sample standard deviation is 2.2. We have n equals 20. The book calls s divided by the square root of n the standard error, and you probably won't hear me use that too much just because it's more vocabulary to deal with, but I'm going to store 2.2 divided by the square root of 20 as SE for standard error. The t-statistic is the sample mean, x bar, minus mu divided by the standard error. Under the null hypothesis, mu equals 5. We assume the null is true. Our t-statistic comes out to be negative 0.813. We compare this to a t-distribution with n minus 1 degrees of freedom. We compare it to a t-distribution with 19 degrees of freedom. Let me graph what's happening. The t-statistic lands here. A t-distribution is always centered at 0, so if the statistic is negative, we look behind it to get the p-value for a two-sided test. We find this area and double it. If the t-statistic is positive, we'll get the area ahead of it, then double it. Our p-value is this area here, and that is 0.4262. This is higher than 0.05, so we fail to reject the null hypothesis. We cannot conclude that the population mean is different from 5, and that's because the p-value is fairly high. There's more than a 40% probability of getting a t-statistic this extreme if the null is true. That doesn't give us much reason to think that the null is false. To get a 95% confidence interval, you use the 0.975 quantile of a t-distribution with n minus 1 degrees of freedom. This number here is the critical value. We multiply it by the standard error. The confidence interval is always centered at the sample mean. The bounds will be the sample mean minus the critical value times the standard error, and the sample mean plus the critical value times the standard error. We are 95% confident that the population mean number of years of piano lessons for children in this city is between 3.57 years and 5.63 years. That was part B of the problem. Part C asks if the confidence interval agrees with the test. Well, remember that a confidence interval is an inverted hypothesis test, so they should agree. The p-value we got was greater than 0.05, so we failed to reject the null hypothesis. Since we are 95% confident that the population mean is within this interval, and our hypothesized mean 5 is in this interval, we would fail to reject the null hypothesis at the 0.05 level based on this confidence interval. So yes, they do agree. In that case, we were given summary statistics. Sample mean, sample standard deviation, and sample size are statistics. But if we have the data itself, we can use R's t-test function. I'm going to use the tree's height data. We'll assume that the trees are a random sample of something, so our criteria will be met. If I want to test if the tree's height is different from 79 feet, by default, this t-test command will do a two-sided test. The only thing I need to tell it is the mu I'm using, because that's 0 by default. I say t-test trees $height mu equals 79. And the output here is giving me the t-statistic, which is negative 2.62. The degrees of freedom are 30. The p-value is 0.0136. That's pretty low, barely a 1% chance we'd see a t-statistic like this. Because it's lower than 0.05, we reject the null hypothesis and conclude that the population mean is different from 79. The output also includes a confidence interval. It's 95% by default. We are 95% confident that the population mean height of the trees is between 73.66 feet and 78.34 feet. And finally, it gives us the sample mean of our data, which was 76. You can access these things with the $sign. In your homework, there's a problem where you'll need to extract the p-value from this. You would go like this, trees, t-test trees $height, mu equals 79, $sign p-value. And that's the p-value. And here's how you would go about it by hand. It's the same as last time. You calculate the t-statistic, then use pt to get the area you're looking for. For a two-sided test, it's going to be this area here, and the p-value is 0.0136, just as before. We can get the same confidence interval. For a 99% confidence interval, we would want to go from 0.005 to 99.5 because that's the middle 99%. You can use this quantile here, or you can set conf level of the t-test to 0.99, and it'll give you the same thing. When you're doing a one-sided test, the alternative determines the direction you look at to get the area. If I'm testing that the mean is greater than 79, I look at everything greater than my t-statistic. This p-value is 0.9932, and that's saying that if the population mean is 79, the probability that our sample gives us a t-statistic at least as big as negative 2.62 is over 99%. This doesn't give us any evidence that the population mean is greater than 79. If the alternative is that mu is less than 79, then the p-value is this area here, and that is 0.0068. And that's strong evidence that the population mean is lower than 79 feet.